thing. If you BA cosine theta, if you went the route of BA cosine theta, you'd be going a little bit farther. You'd be going with respect to time of BA cosine theta. B is not changing. A is D times H, right? So D times H, that's changing. Cosine theta is 1, so it falls out. Then I recognize that D is a distance this way. Okay, that's not, that is actually what's changing, right? So the D is changing, but the H is not. So I pull out that, I get BH. Well, I should get a BL. What's going on here? H. Well, is H. Oh, I didn't switch it here. That's the problem. Good call. Okay, so then D, D, DT, right? Agreed? And how fast is that changing? How much area is getting put into the box? It's the velocity of the thing, right? So it becomes BHV, not, and that would be the way to do it with DA. Again, much easier to remember the actual way to do it with a bar, but if you don't, totally works. It's the same idea. Okay? I'm going to erase this into it because I need some more space. Then it says, what's the magnitude of the initial induced current? So initial induced current is caused by this same thing. It's going to be D dt of BA cosine theta. Agreed? Right? That's my voltage. So B is not changing, A is not changing, blah, blah, blah. I've got my E is equal to V naught HB. Agreed? We just solved for the previous problem. How do I find my current is? V equals IR. So I'm going to go IR is equal to V naught HB. Therefore, I is equal to V naught HB over R. And I'm done with that one. Which direction is the current in? I got two ways to answer this question. One of them, old man way. Current wants to go in a way that reduces what's happening to it. There's suddenly more magnetic field coming out of the board through this section right here, right? So I want to stop that. So I'm going to force current. I'm going to force current in such a way that my magnetic field goes back into the board, right? To neutralize that effect. So if the current's going this way, going upwards, I curl my fingers, that would come out of the board and make it stronger. That's not what I want. So I'm going to turn it over and make it go down. So the current would be this way, which would be clockwise. Agreed? Now keep in mind, you could have done that without actually doing any of the problem, right? You couldn't answer that question by itself. It's probably 2 points in a 15, just for saying clockwise. Does it say explain? Nope, you didn't explain it. Now the other way you could do is this. You could say there's charges in the bar, right? Those charges are going this way. The magnetic field is out of the board, so the current would be down, right? And so you can get it that way too. Agreed? Make sense, Brandon?
Yeah.
Okay. Yeah. So, moving forward, it says derive an expression for the velocity of the glider as a function of time. This one's nasty. Nasty, nasty. Ooh, just awful. Awful, awful, awful. Derive an expression for the velocity of the glider as a function of time for the interval from the front edge of the loop enters the magnetic field, but before the rear end enters the magnetic field. Now, when the rear end enters the magnetic field, what happens after that? Nothing, because you've got a loop this way, the magnetic field is no longer changing inside, so there's no effect at all. So there'd be no current induced at all. I'm just sitting there dead in the water, right? But before it enters the back end, this front is still in play. So why would the velocity change, Brandon?
You have a charge going into the field. Is that
Yeah. I've got a wire though, so instead of saying about charge, what am I actually going to talk about? When I talk about current instead, I'd use a current form of what equation is that? IL cross B, which is the what? Force?
Yeah.
So if I've got force is equal to IL cross B, I just discovered that the current is in fact that. The length of the wire is whatever this dimension is, which I didn't write on the board, which is really dumb, H. The magnetic field is B. So the force would be that, would it not? Agree with that so far? Now, here is the problem. I made a V knot there, but really what's happening isn't that V, and it's changing, right? So that's a problem. Okay? So far with me? So far with me. So now I want to find, what does it say, distance or velocity? And I want an expression for the velocity of the glider. So now I'm going to start monkeying with my force into this. Agreed? So my force is MA is equal to V HB over R HB, right? Now how am I going to deal with the fact that velocity changes my acceleration? You guys remember how to do this? We just started playing with this recently. Acceleration is dv dt. Equals h squared b squared over rv. So, how do I deal with this? V's got to come over here. Everything with a T's got to come over here. I'm going to go ahead and move the M anyways, just because I want a block of constants rather than constants everywhere. So I'm going to move the V over here. I get 1 over V dV equals H squared B squared over Rm dt. Agreed? Integrate both sides. By now I know the drill, right? This becomes ln of V, absolute value, equals H squared B squared over RMT plus C. So then this becomes V equals E to the H squared B squared over RM. I can't even put it all in here. T. And I can put a V right here. With me so far? I'm sorry, B naught, right? Because initial conditions. Everybody said nod their head, but basically that's initial conditions, right? And then I've got one more thing as a physicist we need to look at. And that is I got H squared B squared over RMT. Now this would imply as time goes on, this thing's going to go faster. Oh, wait, he's looking at something. What did I do wrong? I kind of ran out of space. I apologize. Oh, that's what I said. Ever get this? And then I kept going. At that point would be a good time for you to say, no, I don't get. Remember initial conditions? I can swing this down and make it a constant in front because I'm swinging it up to E. So I can make that a constant in front. And if I plug in 0 for T, this becomes 0, which makes E to the 0, 1, which makes the initial condition. Right? I'm going to pause there. Does that make sense? So sort of. Again, if you want to, you can actually solve for it, put the 0 in for T, and then get B naught. That's going to be B naught. Okay, this is wrong. What's wrong with it? The implication is as time goes on, it's going to be going faster and faster. What does magnetic fields do? They resist change. I've got a thing moving into a magnetic field. It's going to resist that change by slowing it down. The other way to do it is you've got current, magnetic field, force is going to be back that way, right? So it should be slowing it down, not speeding it up. So I'm going to fix that. Yes, sir?
We kind of knew that could happen when we had with the absolute value signs, right?
Right. Although really that's not where it's going to come into play, because the velocity knot is still going to be a positive value. Where it comes into play is this acceleration is in the negative direction. So this should have been negative to begin with, which would make this thing negative, right? Which means this would be negative, and that's what I should have done. Okay? Acceleration's in the negative direction. It's slowing me down. If I set velocity to be the positive direction, then acceleration's got to be negative. Wasn't that fun? That one's why I did. That's why I did that one without actually do the problem. But do the last one because it's awesome. Try to flip it over and do the problem in the back. Qualitatively discuss what. And we know it's going to be slowing until it gets to T1. Then once the whole glider's inside, right? So which way is the forces on it? Nowhere. Hey, I've got a glider inside. It's all right. I like this. This is fine. So it's not going to resist change, right? For a little while, because there's no change to be resisted. Once it starts to leave, what's it going to do?
I feel like it's going to get pushed out.
You think so, right? Except that would be change. Is the magnetic field going to increase the change? No, it's going to resist the change yet again. And so it's going to slow the glider down again. Until it's free and clear, in which case it'll go at constant velocity. Yes?
So you made those curves concave up.
Yes.
Should they be concave up?
Yes, because at the very beginning is when they're going to have maximum amount of current flowing into them, right? Because you got the maximum velocity at that point. And if you have the maximum velocity at that point, that means your BLV is going to be larger because your V is larger. Okay. As time wears on, that's going to thin out until there's basically no effect at all. And then as you go, as both wires are now in it, there's no effect at all. The moment you try to leave, one wire leaves, all of a sudden, whoa, hey, we're losing flux. So I'm going to resist that change. And at the beginning, I resisted a lot. By the end, I have no effect on it at all. There's very little change, and my velocity is already slower, so I have less ability to resist the change.
Is that sort of thing that they would look at, or is that kind of
concave? I don't remember what the key is. I'll pop up the key in just a moment. Go ahead and start. We've talked about this enough. You should be able to now try 148 without me too much. So try all 148, and then I'll go through and do that. I'm gonna pop the key. 143, right? Oh, it's recording. Pause. Nope. Would take a changing magnetic field, something that I generally speaking